Okay, so in this lecture, we're going to discuss two radical reactions that occur in a flask, the chlorination and the bromination. Together, we can consider those as radical halogenations, which we introduced in our last lecture. We'll go over those reactions in great detail. And then at the end of our lecture, we will talk about radical reactions of ozone, the ozone layer, which we've alluded to earlier in the class, and radical chemistry that occurs in that area of our atmosphere. So the first thing we'll do with chlorination, and actually this applies to chlorination and bromination because it's the same mechanism, is discuss the mechanism of the reaction. So since it's in chapter 15, you can conclude that it is a radical mechanism. But if you didn't know that ahead of time, you would have to collect evidence and use that evidence to propose a mechanism. So here's some of the evidence that has been collected for a radical mechanism, or a mechanism involving radical intermediates in the halogenation of alkanes. The first point is that light, heat, or a radical initiator, one of those three things is necessary for the reaction to occur. It will not occur in the absence of one of these components. So, or at least, I should say it another way, at least one of these components must be present in order for an alkane halogenation to occur. Light or heat will provide the energy to form the necessary radicals directly, and in some cases we could use an initiator. The second piece of evidence for a radical mechanism is that oxygen inhibits the reaction. In our next lecture, which will be the final regular lecture of the semester, we'll talk about how oxygen can function as a radical scavenger. We introduced the term radical scavenger in our last lecture. It's a species that reacts with a radical intermediate to form a more stable and less reactive intermediate. So if oxygen inhibits a reaction and does not allow the desired products to form, that is very strong evidence that reaction involves radical intermediates. And then the third point is that we do not see rearrangements. So we have the same carbon skeleton in our alkyl halide products of a halogenation that we had in the alkane starting material. So we haven't rearranged the skeleton, we've just replaced an individual hydrogen atom with a halogen. So no rearrangements is evidence against carbocation intermediates. So this is indirect evidence for a radical mechanism, and the first 2 points are direct evidence for a radical mechanism. So with these pieces of evidence, these data, we can construct a mechanism, a proposed mechanism for halogenation of alkanes. And it's going to be a different type of mechanism than mechanisms that we've drawn before. So the net reaction we're going to draw the mechanism for is the chlorination of ethane. So that's ethane right there. We're going to react ethane with chlorine. We're going to require heat or light, although I wrote it as light or heat. We're going to form chloroethane as our organic product. And then we're going to form HCl as the byproduct. So this is the net reaction we're going to draw the mechanism for. And there are 3 steps in this mechanism. So the first step is going to be the formation of radicals from chlorine. Okay? As we heat up our reaction mixture, if we have enough energy present, we will be able to cleave the chlorine-chlorine bond. So we're just going to say, just to keep it simple, we'll just use heat in this example. And that's going to give us 2 chlorine atoms, which are radicals. They each have a single unpaired electron. Okay, and this step has a name. This is referred to as initiation. In a radical reaction, when you convert a non-radical species into a radical species, that process is referred to as initiation. Okay, so step 1 in our radical halogenation is an initiation. You'll notice that as we heat up this mixture of ethane and chlorine, the weakest bond in the system is the one that is cleaved homolytically. The bond dissociation energy for Cl2 is 58 kcals per mole. Okay, I'll just go ahead and write that right here. We'll discuss some of the other bond dissociation energies later on, but the carbon-carbon bond dissociation energy is about 88 kcals per mole. The carbon-hydrogen bond dissociation energy is 98 kcals per mole. So you see that the chlorine-chlorine bond is much weaker than the carbon-carbon and carbon-hydrogen bond. So that's the one that is cleaved when we heat up the reaction mixture. Okay? So once we have our chlorine radicals, if you remember from our last lecture, we said that radicals can abstract hydrogen atoms from alkanes. So our chlorine radical is going to abstract a hydrogen atom forming a carbon or a hydrogen chlorine bond and breaking a carbon hydrogen bond. So we now have an alkyl radical, a carbon-centered radical, and we've now formed a molecule of HCl. So we've formed our byproduct in this step. And then our third step in the mechanism, our alkyl radical is going to collide with our chlorine molecule, Cl2, and it's going to abstract a chlorine from Cl2. So we're going to form a carbon-chlorine bond, cleaving the weak chlorine-chlorine bond. This is not an electron here. This is some sort of a bump in the chalkboard. So hopefully that's not confusing you. That's hopefully not too visible on the video. So when this ethyl radical collides with chlorine, we generate chloroethane, and we form a new chlorine radical. Okay. So what happens to the chlorine radical when we form it? Well, it's going to collide with another molecule of ethane and perform the hydrogen atom abstraction step, generating an ethyl radical, which then collides with chlorine, forming the chloroethane and the chlorine radical. So these two steps repeat over and over again in a chain reaction process. So many radical mechanisms, the ones we're going to discuss in this chapter, are going to be chain reactions, where we have an initiation step that forms radicals from non-radical species, and then the subsequent steps are referred to as propagation steps. So step 2 and step 3 taken together are propagation steps because they are propagating the chain process. In each of these steps, a radical is reacting with a non-radical to form a new radical. And because the radical formed in our second propagation step is a participant in the first propagation step, that is what allows this reaction to be a chain. So this is a chain mechanism. And when we have a chain mechanism, we have an initiation step, and then afterwards we have propagation steps. Okay? So I told you last time that radicals usually react with non-radicals. They don't react with each other very frequently, but it is possible to have two radicals collide. And so in the chlorination of ethane, there are a couple of other things that go on we can have two chlorine atoms collide and reform Cl2, or molecular chlorine. Okay. And that's not a big deal because we continually heat the reaction mixture. So when the chlorine reforms, because of all the thermal energy that's present, pretty soon you're going to be able to cleave that chlorine-chlorine bond and reinitiate the chain mechanism. So that's not a big deal. You can also have two ethyl radicals collide. If that happens, we're going to form butane. And in fact, the formation of a small amount of butane in the radical chlorination of ethane is additional evidence for the radical mechanism. Okay, we do get some butane in the reaction, a small amount formed by this process shown here, and that's evidence that these ethyl radicals are present. Okay, and then we can have an ethyl radical and a chlorine radical collide with each other. And that's going to provide us with another way of getting our final product, our chloroethane. So what's the difference between forming our chloroethane by this method as opposed to this method? What happens by this method is that we terminate the radical chain. We've taken two radicals, we've reacted them to get a non-radical. We have no more radicals, so the chain is no longer propagating. So the reaction would stop unless we had another initiation event occur and we're able to form more chlorine radicals. So these three steps are all referred to as termination steps. So when you have two radicals collide to form a non-radical product, you are terminating the chain reaction. And they're much less frequent than the propagation steps and even the initiation step because the concentration of the radicals is always low. But they will happen. So a small portion of our chloroethane that forms in this reaction will come from the termination process. We will get a small amount of butane in there, and we can detect that, and that's evidence of the radical mechanism. And then we'll also reform some chlorine, but that's okay because we can reinitiate and we can just cleave that chlorine-chlorine bond. So the propagation steps usually occur thousands of times for every one time that we have a termination step in a radical process. And when we're drawing radical mechanisms, we don't have to draw the termination steps because they are so rare. We usually only draw the initiation and the propagations, okay? So terminations, it's important to know that they exist, but if you're asked to draw the mechanism of radical chlorination, you could draw these three steps and ignore the terminations. Okay, so let's look at the changes in energy that occur during our two propagation steps in the chlorination reaction. So I'll redraw those steps here on this board. In our first propagation step, the hydrogen atom abstraction step, to determine the delta H, we need to compare the bond dissociation energies of the bond that is broken with the bond that is being formed, okay? So we're breaking a carbon-hydrogen bond, and the bond dissociation energy of this carbon-hydrogen bond is 98 kcals per mole, okay? So that's a pretty strong bond that we're breaking. And I'm going to put a plus sign in front of that value because since we're breaking that bond, we have to put energy into the system to accomplish that. The bond that we're forming is this hydrogen-chlorine bond. And that's actually a stronger bond than the carbon-hydrogen bond, 103 kcals per mole. So I'm going to put a negative sign in front of that since we're forming that bond. That's going to release energy. So the net delta H for this first propagation step is going to be negative, minus 5 kilocalories per mole. Okay? It may seem surprising that the HCl bond is so strong, given that HCl is a strong acid and that bond is cleaved readily in acid-base reactions. Remember that bond dissociation energy involves the formation of radicals. It's a homolytic process, which is very different from an acid-base reaction. So it's completely possible for a strong acid to have a strong bond in it. And that's what we see here in this radical reaction. Let's just raise this up a little bit. And we'll draw our second propagation step here, and we'll analyze the energy. In propagation step 2, we take our ethyl radical and we react that with our chlorine, molecular chlorine. We're breaking a chlorine-chlorine bond, and we're forming a carbon-chlorine bond. Okay? And I mentioned to you earlier on that chlorine-chlorine bond is the weakest bond of all the bonds present in the reactants, as well as the products of this reaction. It's 58 kcals per mole. And we'll put a plus sign in front of that because that's the energy that is required to break that bond. And then the bond that we are forming is a carbon-chlorine bond. That bond is not as strong as the carbon-hydrogen bond, but it is still a strong bond, 81 kilocalories per mole, significantly stronger than the chlorine-chlorine bond that is breaking. We put a negative sign in front of that value, indicating that we're forming that bond. That's the amount of energy released by forming a carbon-chlorine bond. So if we do the math, our second propagation step, highly exothermic, 23 kilocalories per mole. And then the overall, delta H naught, delta H overall is going to be minus 28 kcals, running out of room here, per mole. Okay? So in the chlorination reaction, both propagation steps are exothermic, and the overall process is therefore exothermic. We're going to look at a potential energy diagram for this reaction. And we see two intermediates, two transition states, two maxima indicate two transition states. We're just considering the propagation steps here. We're not considering the initiation step. And then our intermediates is going to be our alkyl radical here. Our product is the chloroethane in the chlorine radical. We see that the energy of activation for step 1 for the hydrogen atom abstraction is higher than the energy of activation for step 2. So that tells us that the rate determining step of a chlorination reaction, and it'll be the same for bromination, the rate determining step is the first of the initiation steps. The hydrogen atom abstraction step is the rate determining step in halogenations. Okay? But both steps are exothermic. So now what we're going to do is we're going to look at an example of a chlorination where more than one product is possible. So let's take propane. We're going to react propane. We'll use light this time. We could use heat or light. Reacting it with chlorine. we have two different types of hydrogens in propane. And so that means we have two different types of alkyl chlorides we could obtain, the primary alkyl chloride or the secondary alkyl chloride. And it turns out that when you perform a chlorination reaction, you get a one-to-one mixture of these two products. So why do we obtain a one-to-one mixture? If we look at our mechanism, which we can see here on this board, or we can see it on the screen, either place, we see that the step that determines which product is formed is our first propagation step. Our chlorine atom, the radical chlorine atom, is going to abstract a primary hydrogen from propane to give us the primary alkyl chloride, or it will abstract a secondary hydrogen from propane, and that will give us the secondary chloride, isopropyl chloride in this case. So it is a difference in that first propagation step that is going to dictate which of these two products is formed. So if we look at propane, we have 6 primary hydrogens. We have 3 on this carbon and 3 on this carbon. We only have 2 secondary hydrogens, the methylene, the CH2 here at carbon 2. So when a chlorine radical collides with propane, it's 3 times more likely to collide in an orientation that will cause abstraction of the primary hydrogen as opposed to the secondary hydrogen. So statistically speaking, we would expect 3 times as much of the 1-chloropropane to form as the 2-chloropropane to form. But that's not what we see. Instead of seeing a 3-to-1 ratio of these products, we see a 1-to-1 ratio. So what that tells us is that the secondary radical is formed 3 times faster than the primary radical. Okay. So I'll repeat that. Statistically, since there are 3 times as many primary hydrogens than secondary hydrogens, we would expect a 3-to-1 ratio of these products. Since we're getting 3 times as much of the secondary alkyl halide as we would expect from statistics, that means that the secondary radical must be formed 3 times faster than the primary radical to counteract the statistic effect and give us this 1-to-1 ratio. So the question becomes why? Why are we forming the secondary radical 3 times faster than the primary radical? This goes back to the Hammond postulate. So here we have our propane, we have our chlorine radical, we have 2 reaction pathways leading from these species. One, the red pathway leading to the primary radical, plus HCl. The second pathway, the blue pathway leading to the secondary radical, plus HCl. Okay? And so this is an exothermic step. It's only slightly exothermic. So the transition state is going to more closely resemble the reactants, which would be the chlorine radical and the alkane, than the products. But because it's not too exothermic, you're going to have a decent amount of radical character on the alkane at the transition state. Okay? So you would have maybe 30% of a radical, just to throw a number out there. You'd have about 30% of an alkyl radical present at the transition state. So even though the transition state resembles the alkane more than it resembles the alkyl radical, you do have a fraction of radical character at the transition state. Since the more stable radical, or the more substituted radical is more stable, The transition state leading to the secondary radical is going to be slightly lower in energy than the transition state leading to the primary radical. So this difference in energy causes the secondary radical to be formed faster, but not that much faster. You might think 3 times faster is a lot, but in organic chemistry, you'd have to have a difference of 100 or more before we would say there was a huge difference in those reaction rates, okay? So for our purposes, there is a difference. The secondary radical is formed faster, but not that much faster. The difference is only enough to counteract the statistics. If you look at the structures of organic molecules, our less substituted carbons are always going to have more hydrogens on them. So statistically speaking, you would be more likely to form less substituted radicals. The difference in radical formation in chlorination is just enough to counteract those statistics, to make it so that you're forming all the possible radicals in roughly equal reaction rates, okay? So what that means is that in a chlorination reaction, we're going to form all possible products, all possible chlorination products, and we're going to form them in roughly equimolar amounts. There will be small differences, but for our purposes, to simplify things in the class, when we're performing a chlorination of an alkane, we will form all possible products in essentially equimolar amounts, okay? And that is due to the difference in rates being slight, since the hydrogen atom abstraction step is exothermic. According to Hammond's postulate, this transition state looks more like the reactants than the products. It only has a small amount of radical character, just enough to counteract those statistics and give us these equimolar mixtures. So, what that allows us to do is ask questions like this, okay? So here we have 2 iClicker questions. How many monochlorinated products would you expect from these 2 compounds? We have the same list of answers. To simplify things, we've allowed you to ignore stereoisomers. We're only asking you to tell us how many different constitutional isomers would be formed by monochlorination of these 2 products. So go ahead and pause the video, answer both questions, and once you've come up with those answers, press play again, and we will discuss the questions. Okay, so if we, basically what this question is asking us is how many different types of hydrogens do we have in this molecule? And if we look at number 1, the methyl groups are all equivalent. There's no hydrogen here. You cannot chlorinate on this carbon because there's no hydrogen to be abstracted. And then we have this CH2, which is different from that CH2, and then the methyl group at the end. So we have 1 represented by these 3 methyls, 2, 3, 4. So you would get 4 different constitutional isomers by chlorination of compound number 1. Compound number 2, we have symmetry. We have a plane of symmetry that goes diagonal from right to left. And so that means we have our methyl group, that's 1. Our methine, or CH, that's 2. These carbons are equivalent, that's 3, 4, and 5. Okay, so the answer would be C. Now, if we'd asked you to consider stereoisomers, the number would be much bigger. And some problems do, others don't. So when you're asked how many monochlorinated products you would expect, make sure you read the problem carefully to see if it's asking you to just come up with constitutional isomers, or if it also is asking you to consider stereoisomers, meaning diastereomers and or enantiomers. Okay? But in this case, we're ignoring that. We're just counting the constitutional isomers. Okay. Now we're going to talk about the bromination reaction. And first, we're going to talk about differences between chlorination and bromination. The mechanism is the same. So we're not going to draw the whole mechanism out, but there are two key differences. One, chlorination is faster than bromination. The difference is actually pretty significant. I don't have an exact number, but it is probably more on the 10 times faster or more. It's a pretty significant difference in reaction rate. Okay, so bromination is going to be much slower. The second difference is bromination is much more selective, whereas chlorination will give you all possible monochlorinated products. Bromination will give you a major product. So if we're performing a bromination of propane, we've got the same two possible products that we did with the chlorination of propane, except we have bromine instead of chlorine. Instead of getting a 1-to-1 ratio, we form almost exclusively the more substituted bromide. It's going to be a 99-to-1 ratio. Okay? So let's back up a minute before we go through this. One other thing I should say about chlorination is that since chlorination gives you all possible products, and usually you only want one product from a reaction, chlorination will be most useful when there's only one type of hydrogen in your molecule. And the most common molecules that have one type of hydrogen are cycloalkanes, cyclopentane, cyclohexane. Methane has one type of hydrogen. Ethane has one type of hydrogen. There's a few others. But chlorination is going to be most useful for molecules that only have one type of hydrogen. Whereas bromination is going to be selective and allow you to generate the more substituted bromide. So we have the same statistics here. We have 3 times as many primary hydrogens as we do secondary hydrogens. And so the fact that this ratio is basically 100-to-1 tells us that with bromination, the formation of the secondary radical is about 300 times faster than the formation of the primary radical. It was 3 times faster in chlorination. It's 300 times faster in bromination. So you have a much bigger difference. Okay? So to understand that difference, we need to look at the thermodynamics, the delta H's, for our 2 propagation steps. We did this for the chlorination. Now we need to do it for the bromination because we're making and breaking different types of bonds in this case, right? So in propagation step number 1, we're breaking a carbon-hydrogen bond. That's the same as what we did before. But we're forming a hydrogen-bromine bond as opposed to a hydrogen-chlorine bond, okay? So we know that this bond dissociation energy is 98 kcals per mole. We saw that with the chlorination. The hydrogen-bromine bond is significantly weaker than the hydrogen-chlorine bond. Bromine is a bigger atom than chlorine. There's a longer bond, and so it's weaker, 88 kcals per mole. Okay. So our first propagation step is endothermic. Endothermic by 10 kcals per mole. Okay. Let's look at the delta H of the first propagation step to form the more substituted bromide. I didn't draw that very well. There we go. So the bond dissociation energy for a secondary carbon-hydrogen bond is 95 kcals per mole. We learned that in our last lecture. We already know the HBr bond is 88. So the first propagation step to make the secondary radical, which leads to the secondary alkyl bromide, is going to be endothermic by 7 kcals per mole. Okay? So we remember from Hammond's postulate that if we have an exothermic step, the transition state resembles the reactants. But if we have an endothermic step, the transition state resembles the products. So here we have the energy diagrams for these two propagation steps that I drew for you, both of them originating from propane and a bromine atom. The red pathway is leading to the less substituted primary radical. The blue pathway is leading to the more substituted secondary radical. And as we know, the secondary radical is more stable, lower in energy than the primary radical. In contrast to the chlorination, since this first propagation step is endothermic, these transition states more closely resemble the alkyl radicals than they do the alkanes. So at the transition states, you would have 60 to 70% of a radical, just to throw a number out there. So with that increased radical character, you have a bigger difference in energy between the transition states in the bromination than you do between the transition states in the chlorination. So that bigger difference in energy leads to a much bigger difference in reaction rate. That leads to the 300-fold difference in reaction rate. Let me just go ahead and write that on the board here. Secondary radical formed 300 times faster than primary radical. So that much bigger difference in reaction rates is reflective of a much bigger difference in energies of the transition states of those two different first propagation steps. Okay? And that's due to the transition states in the first propagation step of bromination resembling the radical intermediates, or the product of that step. In contrast, the transition states in the first propagation step of the chlorination, since it's exothermic, resemble the alkane starting materials and only have a small amount of radical character and therefore have a small difference in rate. Okay? So, to understand the differences between chlorination and bromination, the fact that chlorination gives all possible products in roughly equimolar amounts, whereas bromination is selective for the more substituted product, we have to understand Hammond's postulate. So this is a good review of Hammond's postulate. And we also have to analyze the energies, the delta H of those first propagation steps and recognize that they are exothermic in the chlorination and endothermic in the bromination. Do we have? Okay, we don't have it. We don't have a diagram for both propagation steps of the bromination, but I will tell you that the second step in the bromination is indeed exothermic. Okay, so if you look at the bond dissociation energies in the second propagation step of the bromination, where our alkyl radical is abstracting a bromine atom from bromine and breaking the bromine-bromine bond, that carbon-bromine bond that forms is stronger than the bromine-bromine bond that breaks. Okay, so the overall process of bromination is still exothermic because the second propagation step is exothermic. It's only the first propagation step, as we've drawn over here, being endothermic. Okay? So this also explains why the bromination is slower than the chlorination because the activation energy for the first propagation step is higher than the activation energy for the first propagation step in the chlorination. Okay? So in practice, chlorination is good only when we have alkanes where all the hydrogens are equivalent. Bromination is good if we want to form secondary or tertiary bromides because the rate for forming a primary bromide would be really, really slow. So we're only going to get secondary or tertiary bromides. But what would you use these reactions for in the real world in terms of multi-step synthesis? So bromination and chlorination are quite useful because they allow us to convert alkanes into alkyl halides. So let's say you had cyclohexane, and you needed to convert cyclohexane into cyclohexene. How would you do that? We don't have a method of just plucking two hydrogens out of cyclohexane and generating that alkene. We don't know how to do that. So we would have to do a multi-step synthesis. So we would do a retrosynthesis. We would look at our alkene and we would say, okay, what is an immediate precursor to an alkene? We actually have a few. To save you some time, I'll come up with the one that is relevant to this problem. We could obtain an alkene from dehydrohalogenation of an alkyl halide. And now, in this chapter, we've now learned how to obtain an alkyl halide from halogenation of an alkane. Okay? So in the synthetic direction, we could take our cyclohexane, react it with chlorine. We'll use heat this time. We only have one type of hydrogen atom in cyclohexane. So we're only going to get a single product in this case, chlorocyclohexane. Note that you could use bromination because bromination works fine to make secondary alkyl halides. But if I was doing this, I would choose the chlorination because it'll be faster than the bromination. Okay. And then whenever we want an E2 reaction to occur, potassium tert-butoxide is the base we know that's going to promote that. Okay. So anytime you're asked to perform a multi-step synthesis and you have to start with an alkane, you're going to want to use a halogenation because that's the only reaction we know of to introduce a functional group on an alkane. And you're going to choose bromination or chlorination depending on the type of alkane that you're starting with. All right, let's talk about how stereochemistry is involved in halogenation reactions. So this table here reviews the relationships between starting materials and products in terms of stereochemistry. You know that if we have an achiral starting material, we're either going to get an achiral product or a racemic product if we're forming a chiral product. Of course, there is an exception here. We could say unless we have a chiral catalyst, but this is assuming there's no chiral catalyst involved. If we have a chiral starting material, if the reaction's occurring at a site other than the stereocenter, then that stereocenter is going to be undisturbed. But if the reaction's occurring at the stereocenter, we have to understand the mechanism of the reaction to be able to predict the outcome. So let's see how the information in this table applies to halogenation reactions. Let's start with an achiral starting material. Here we have butane. And we're going to chlorinate butane. We have two types of hydrogens, and so we have two different products that are going to form, two different constitutional isomers, okay? 1-chlorobutane, that's achiral. Okay, so we don't have to worry about stereochemistry. Of course, we started with an achiral alkane. True to form, our table tells us that we're going to get either an achiral product or a racemic product. So here's our achiral product. We could chlorinate at carbon 2 and get 2-chlorobutane. That's going to be chiral, so we're going to have to form that as a racemic mixture. Okay? So we generated our achiral product, and we generated our racemic product. Okay? The radical we form is going to be planar. The secondary radical will be planar. So the chlorine will approach with the same rate from both sides, giving us a racemic mixture. So in this case, we would expect essentially a 1-to-1 mixture of the achiral to the racemic. And so we would actually have less of each enantiomer than we would of the achiral product. But it would be a 1-to-1 mixture of racemic to achiral. Okay? But what if we're halogenating a chiral product, or chiral starting material, I should say. So let's say we have 2-bromobutane, and we're going to chlorinate that. And I'm just going to skip ahead to the propagation step. So I'm going to react our 2-bromobutane. I'm going to move this lone pair down so it doesn't look like we have 3 electrons. Sorry about that. So we're going to abstract the hydrogen. So now we've taken our chiral bromide, we've reacted it at the stereocenter. We formed HCl in the process. So now we have an achiral radical intermediate. Just to save time, I'm not going to draw the arrows in this next step, but that's going to abstract a chlorine. The chlorine is going to approach with the same rates from the top and the bottom, and so we're going to get a racemic mixture of this bromochlorobutane. Okay. So if we're performing a halogenation at the stereocenter, the product is going to be racemic because we destroy the stereocenter in the process. If the reaction occurs at a different carbon, oops, I added another carbon on, sorry. Okay, so let's say we abstract one of these hydrogens. We're forming HCl. We have our radical here. So now we haven't touched our stereocenter. We're going to abstract a chlorine atom from molecular chlorine. The chlorine can approach from either face. You might say, well, one face is more hindered than another. Not exactly, because we have free rotation about this carbon-carbon bond. So this bromine is not going to hinder one side of that radical more than the other. So what's going to happen in this case is we're going to form a 1-to-1 mixture of products. But because we have not touched the original stereocenter in the starting material, we've only formed a second stereocenter. These products are diastereomers of each other, okay? All right, so we form a one-to-one mixture of these diastereomers. So if you're performing the halogenation of a chiral alkene, if the reaction occurs at the stereocenter, you generate a racemic mixture. If the reaction is occurring somewhere other than the stereocenter, you're going to generate a mixture of diastereomers. Okay? So a lot of things to consider when we think about stereochemistry of radical reactions. All right. The last thing we're going to talk about today is the radical chemistry of the ozone layer. So we've mentioned ozone previously in the class. The ozone layer protects us from UV radiation by converting that UV radiation into heat. Okay? So ozone, there's a couple different resonance structures we can draw of ozone, but we can draw a diradical version of it. Okay? So we can draw ozone in this fashion. And if we have UV light, that UV light is going to break ozone up into an oxygen molecule and an oxygen atom. And then the oxygen molecule and the oxygen atom can recombine to reform ozone. And because the only thing that's happening in that step is a bond formation, that's going to be exothermic and heat is given off. Okay? So it's a simple and ingenious way of taking ultraviolet light, which is very harmful to us, and converting it into heat. Okay? So that's what the ozone layer does. And it was doing that for millions of years, hundreds of millions of years, until humans came along and created chlorofluorocarbons. Okay? We talked about these back in chapter 7, maybe? I can't remember exactly. But our chlorofluorocarbons were used as refrigerants. They were used as aerosols. They were ejected into the atmosphere. And then decades after we were doing this, we discovered that they were destroying the ozone. This slide here shows how chlorofluorocarbons destroy ozone. The carbon-chlorine bonds in these molecules are weak, and so when they are exposed to light, they undergo homolytic cleavage, generating a chlorine radical. The problem is that the chlorine radical can react with ozone. It can pluck an oxygen out of ozone, giving you this OCl radical. That OCl radical can react with oxygen atoms. Remember, oxygen atoms are going to be present in the ozone layer because your ozone is continually being broken up and then being reformed. And this can intercept that oxygen atom to form another chlorine radical. So what you see is that the net result of these propagation steps is the destruction of ozone. We're destroying O3. We're pulling out the oxygen radicals, oxygen atoms that are needed to reform that from O2. So we're depleting the ozone, and because chlorine is produced, chlorine atoms are produced by the second of these propagation steps, this process is catalytic in chlorine. A single molecule of a chlorofluorocarbon can destroy thousands of ozone molecules. Okay, so this is a problem. This chemistry was discovered in the 1970s in the lab, and then it was verified in the 1980s when the ozone hole was detected over Antarctica. So, how have we been able to reverse this? Well, we stopped using chlorofluorocarbons, and we replaced them with hydrofluorocarbons. hydrochlorofluorocarbons, HCFCs, or HFCs. So what we do is we use longer chain molecules that still have fluorine or chlorine in them, because those are good as refrigerants and good as aerosols, but they have carbon-hydrogen bonds. Paradoxically, the HCFCs and the HFCs are less stable than the CFCs to light. What that means is that they will react lower in the atmosphere by radical mechanisms and be destroyed lower in the atmosphere before they make it up to the ozone layer. Okay, so the CFCs, this carbon-chlorine bond was weak enough to be cleaved by light, but strong enough that the CFCs make it all the way up to the ozone layer before that cleavage occurs. So paradoxically, we used molecules that were less stable, and that was beneficial because they're able to be destroyed before they make it to the ozone. So that has allowed the ozone layer to heal. It's not totally healed. The ozone hole still appears over Antarctica every year, but the ozone hole is healing as the concentration of the chlorine radicals in the upper atmosphere continually decreases as we're not releasing any more of these CFCs. Okay. All right. So that concludes our lecture for today, and our next lecture will be our final lecture. We will conclude chapter 15.